Good evening and welcome back to AP Stats Notes Online. Going to wrap up Chapter 3, Regression Analysis tonight. And can do so, I think, pretty quickly. So let's start with the next page in your notes, which, again, R squared, S, these are things that you're not going to have to calculate. Creating a scatter plot, creating a residual plot. Again, you're not going to have to create, in terms of a test setting, AP exam or a test in here. Fact of the matter is, and I keep saying this, you only have a certain amount of time in which to take these tests. And so punching buttons in your calculator is a complete waste of that time. So you're not going to have to do that. Now, I have seen some, again, just a reminder, some AP exam questions that actually have you draw the least squares regression line. And so you should be able to do that, but that's plotting a couple of points and drawing a line, which is Algebra 1 stuff, and so hopefully is not too terribly difficult, but make sure that you can do that. Outside of that, that's about the only creation you're going to have to worry about. Instead, what you'll find is a situation like this example, fresh flowers. For their second semester project, 2 AP Stat students decided to investigate the effect of sugar on the life of cut flowers. So they went to the grocery store, picked 12 carnations at random. They seemed equally healthy. When they got home, the students prepared 12 identical vases with exactly the same amount of water in each vase. They put 1 tablespoon of sugar in 3 vases, 2 tablespoons in 3, 3 tablespoons in 3, and in the last 3, they didn't put any sugar at all. So after the vases were prepared and placed in the same location, the students randomly assigned 1 flower to each vase and observed how many hours each flower continued to look fresh. A scatter plot, residual plot, and computer output from the regression are shown. Now you'll be given these 3. The scatter plot with or without the regression line, you may have to draw that in, but you'd be given the scatter plot, the residual plot, and then this. This is computer output. Minitab, Fathom are 2 common statistical software programs. As a matter of fact, I'm friends with a couple of guys from Cummins, which is the auto manufacturing plant in Columbus. In a manufacturing setting, Minitab is used all the time. Anytime you're trying to improve on the efficiency of something, Minitab is pretty powerful for that. But anyway, this is an output from Minitab. And you'll be given this, and it might come from Fathom, and we'll see some computer outputs from Fathom too, but the only thing we got to worry about right now is where do we pull all the information we need from here, okay? For example, what is the equation of the least squares regression line? Define any variables you use, okay? Well, which one is the explanatory variable? Which one is the response variable? We should be able to figure that out pretty quick. We're trying to use the amount of sugar in the water to influence how long a carnation stays fresh. So the equation, least squares regression line, should look something like this, right? So we know it's going to be freshness hat, and I'm going to go ahead and put the variables in here, so I don't have to worry about defining them later. Freshness hat equals. Well, I've got to have a y-intercept and I've got to have a slope. I'll leave some space for that and then come out here and just put sugar for my explanatory. Now you can do it this way, or you can make the equation y hat equals whatever x, and then come over here and say that y hat equals this and x equals this. As long as when you say y hat is the predicted y, right? Again, you have to define what y is. I like this. It takes care of both of these requirements, the equation and defining the variable. So where do we get our stuff? Well, we know that the slope is just the coefficient on our x. It's just the coefficient on, right here, our sugar. So if you look in this box here, we see a column called coefficient. There is a column called SE coefficient, but we're not going to worry about that right now. All we're concerned about is our coefficients. And apparently the coefficient on sugar is 15.2. that is your slope, right? So this is your slope, okay? Now, what might not make as much sense is that there's something that is called a coefficient on a constant, which is weird. Just makes it a constant. And so that constant is 181.2. That is going to be your y-intercept, okay? And so there's your regression equation from that computer output, okay? It comes from right there. Again, you're not going to have to come up with that stuff. It'll be given to you. The next question, and this actually, the format of this whole example is a pretty good idea of what you might see on the AP exam. And so this guy right here is going to be our y-intercept. I'm going to end up marking up this box pretty good. So you might want to do the same, or you might want to find a better way to do that, but to mark all these things. But where are you going to find all this stuff? Okay? What is the correlation? And then interpret the correlation. I want to help you find it, but I want to let you try to interpret it real quick before I show you what I've done. So you look through all throughout this box and try to find anything that might lead you to the correlation. Last thing I want to do is try to type in these data points and then run the regression in my calculator, because this is going to have to be estimates and it's going to be off. So I look into this minitab output, and I look, there's coefficients, SE coefficients, T and P, neither one of those are R, so no, that can't be it. There's an S, there's an R squared, SQ means squared, that sounds really familiar. I know that R is simply R squared square rooted, so how about we try and do that? R squared apparently is 0.86 is a decimal, so let's just square root that guy. And so R ends up being 0.93. Okay? So that's how you're going to find your correlation, because R squared is simply right there, cleverly disguised as R squared. Okay? Now, take a quick second and interpret that. If you want to stop the video, you can, or just try to write pretty quickly. Okay, what'd you come up with? R being 0.93. Well, first of all, when you square root a number, this isn't exactly mathematically correct, right? When you square root an equation, we know that that value could be either positive or negative, right? So the fact that I just wrote down 0.93 real quick, there needs to be some discussion on that. Why is it positive? Why do I know it's positive? Well, take a look at your scatter plot, right? Obviously, your data points are going up and to the right, so R is going to be positive. So we're good here. What does that mean? Well, if R is positive in 0.93, then it lets us know this. It lets us know that there's a strong, linear, positive relationship between the amount of sugar used in the water and flour's freshness. Okay? Or length of flour's freshness might be a better way to say that now that I'm looking at it. Okay? But that's what it means. And you've got to include your context. You've got to include what the situation is that we're talking about. Okay? All right. Next question. Is a linear model appropriate for this data? And we're up here now, right? Is a linear model appropriate for this data? Well, what are we looking at? Well, we do have a residual plot, right? And so I'll let you take a couple of seconds and think about that. Are we okay using a linear model to try to figure out if sugar is going to affect how long our flour stays fresh? Okay, are you thinking about it? What are you thinking? Are we going to use the linear model here? Are we okay using this linear model? Well, is there a clear curve pattern to the residual plot? No. Are the residuals relatively small? Your largest residuals are right around maybe 12 or 12 and a half hours. Okay? You look at your range on your Y value over here in the scatter plot, and that's pretty small in comparison to what your actual Y values are in. So, yeah, I think the linear model here is appropriate. Okay? And so you'd say, to answer this question, right, and it says explain, so what we were talking about before, right, with race, answer the question, look for supporting evidence, and then explain. So yes, the linear model is appropriate. The residual plot does not show a clear curve pattern. And the residuals are relatively small, right? That's our backup. That's our supporting information. A quick explanation, what we mean by the residuals are relatively small. Like what I just said, the biggest residual looks to be around 12 hours or so, which is fairly small in the range of values for the freshness of the flowers. Okay, so that's what we're looking for. Next question, calculate and interpret the residual for the flower that got 3 tablespoons of sugar and lasted 222 hours. Well, we do have our regression equation, right, which was again, freshness hat equals, we'll go back, 181.2 plus 15.2 times the amount of sugar. Okay? And then we have to remember that a residual is simply the actual minus the predicted. So right now we know the actual is 222. I need to know the predicted. No problem. So we plug in 3 tablespoons in here. Do the calculation. Do your button pushing. And if you're doing that now, then I'll talk slowly so that you can try to get there. But you should come up with about 226.8. Okay? That's your actual. That's your predicted. Your actual amount of hours of freshness was 222. So we're going to subtract those and get a residual of negative 4.8. Okay? Interpret that residual. Again, give yourself a second, stop the video, write that out. Okay, what'd you come up with? You should have said something like, let's see if this worked out. I did write over a little bit, but the linear model over-predicted the length of freshness by 4.8 hours. That would work. Okay? Include your context, and over-predicted what, and by how much. Okay? Next question, interpret S. Well, it would be really, really nice if we knew what S was. Okay, again, you're not going to have to calculate it, so let's go find it. And if we arrow back to our computer output, S is cleverly disguised as S. Okay, this is your standard deviation of the residuals, so it's about 7.5. Okay. So S here is 7.5. That's where you get it from. Okay, again, it's just sitting right down here. Okay, standard deviation of the residuals. Interpret that. Take a second and give it a shot. Stop the video, then play it, and we'll see what you come up with. Okay, what'd you say? Did you say something like this? On average, a prediction from this linear model will be off by 7.5 hours. It wouldn't hurt. I don't think we talked about this, but always looking to make your explanations better, right? On average, a prediction of freshness or length of freshness, I don't think you have to include that, but that'd be nice to have. But anyway, from this linear model, will be off by 7.5 hours. Okay? And then last question, interpret R squared. We already know where R squared is. We've already used it. R squared was just right here as R squared. We're not going to use R squared adjusted. That's for later. But for right now, our R squared is 0.86, right? What does that mean? We just did this in homework today, and R squared being 0.86 simply means, again, stop the video, try your interpretation, see what you come up with. Did you say that R squared was 86% of the variation, or you can use the word change, 86% of the variation in freshness is accounted for by the linear relationship with the amount of sugar in the water. And that would be sufficient. Okay, 86% of the change in the length of time of freshness is accounted for. That means 14% of that variation is due to factors that we're not considering right now. It's just another way to look at it. Okay, so all in all, does it make sense to suggest that sugar might affect the length of freshness of flowers if you put sugar in the water? Certainly seems to. Okay, I'm really careful about how I word that stuff, and we'll get to that in just a minute. Okay, but that's where you're going to find all your information from the Minitab output. I'll put you guys in groups tomorrow and give you some outputs from Fathom and things you can look at too, so you can be familiar with those in case those come up on the AP exam. Okay. Now, some last thoughts about regression. Okay, and so your last page here. First question: doesn't matter which variable is x and which is y. Well, it's certainly important to understand which variable is the explanatory and which one is the response in terms of talking about any relationship that we might get. But if we travel back and talk a little bit about how we get R, right? Basically, your equation was this. Right, so we're going to multiply the z-score on an x times the z-score of the y, do that for all of our points, add up all those products and divide by n minus 1, and that will get you R. Well, if we flip-flop x and y, is it going to affect correlation? Can we do z-score on x times z-score of y? Is it going to be the same thing as the z-score on y times the z-score of x? The answer is it's going to be the same. So switching doesn't affect correlation. Okay? So in other words, switching doesn't change the strength of the relationship. It doesn't even affect how much of the change in y is accounted for by the linear relationship with x. In other words, R squared, right? Because if it doesn't affect correlation, if it doesn't affect R, then when you square R, you're going to get the same thing. So it's not going to affect R squared either. But if you go back to your formulas for slope and y-intercept for regression equations, it might may or may not be surprising. It may be surprising that switching the variables doesn't affect the correlation of the strength. So it may not be surprising that it actually does change the regression equation, right? Unless the standard deviation on y is the same as the standard deviation on x, and the y bar and x bar are the same, then the regression equation will change. So the least squares regression equation will change. But the relationship will not. The strength of the relationship will not. So it's definitely important in terms of describing the relationship to know which is which. But in terms of the scatter plot itself, it doesn't change a whole lot. Just changes the equation that we use to make our predictions and whatnot. And that makes sense because our regression equation is trying to predict y. And if we change what y is, then it should change our equation. Okay? Next question, what should you always do before calculating the correlation of the least squares regression line? We'll answer this question in class on Thursday. So hang on to that. There's a nice little activity I want to have you guys do. Next question, does association imply causation? I don't know, how many times have we said it? Right? Does association imply causation? No. And if you're reading in your book, at the very end of chapter 3, the very end of this section, there's a case study or a situation where, an example here where a study once found that people with 2 cars live longer than people who only own 1 car. And if you own 3 cars, then you're going to live even longer, and so on and so forth. So there seems to be a relation between the number of cars you own and how long you're going to live, right? That sounds like a Bob and Tom study there for you, if you're listening to that show. But so does that mean that we need to go out and buy 5 cars and own 5 cars all the time so we can live as long as we can possibly live? Hopefully you're thinking to yourself, well, that's ridiculous. Because it is. I mean, there could be any number of explanations as to why that is. People that buy more cars may have more money and therefore can afford better health care. I mean, it could be anything. So obviously association does not imply causation, no matter how strong your R or your association is, right? Last, what is an outlier? What is an influential point? What is the difference between these two? An outlier just deviates from the overall pattern, right? We've used the term outlier before, right? It's anything that if your relationship is positive, so as X increases, Y increases. If you have a point that seems to be outside of that pattern, right? For a low X, Y is high, or for a high X, Y is low. For a positive relationship, and then it would be vice versa for a negative one, then that's going to be an outlier. Now, we know that, so that's what an outlier is. We know that outliers affect correlation, for sure. And we've talked about that before, and it can affect it a great deal, right? Especially if the outlier is in the Y direction, as opposed to the X direction. And I'm going to show you what I'm talking about in just a second. What is an influential point? An influential point is any point, if removed, will markedly change your calculations. Okay? And what's the difference between these two? Well, let's talk about that a little bit in terms of one of our applets that we were using before. Okay, so here's the applet that we were using before. I'm going to add some points here. And so there you go, a correlation coefficient of 0.8. We know that if you add an outlier, so something that deviates from the pattern, so as X increases, Y is supposed to increase as well over the positive relationship. Well, if X increases and we get a low Y, then obviously it changes the correlation quite a bit. And that's definitely an outlier. It deviates from the overall pattern, right? Doesn't really matter where the outlier is, it's still going to move the correlation quite a bit. If I move it up here, it's still going to drop it by quite a bit because it was 0.8 to begin with. Okay? Now, what we talk about with outliers is an outlier in the X direction or an outlier in the Y direction. And here's what I mean. If we calculate the mean on X and the mean on Y, we know that, we've done this before, we get these two lines that intersect. And for this particular scatter plot, it intersects here. For an outlier to be an outlier in the X direction, then it would be away from the X bar line. And for an outlier to be an outlier in the Y direction, it would be away from the Y bar line, right? Well, as far as correlation goes, if it's an outlier in the X direction, an outlier in the Y direction, it's still going to affect correlation by quite a bit. If it's an outlier solely in the X direction, it's still going to affect correlation quite a bit. So outliers affect correlation, we know that. Question is, what about the regression line? So there's your regression line, right? If I place an outlier in the X direction, well, well, sorry, in the y direction. If I get away from y bar, but I'm not an outlier in the x direction, so I'm going to be on the x bar line, right? I'm still away from the overall pattern. Look what happens. Okay, watch that again. If I do this again, watch what happens to the line. It just gets pulled up. That's it. Right? So the slope of the line hasn't changed, but the y-intercept has. Okay? So it does change a little bit, just not a lot. Now, look at what happens when I create an outlier in the x direction. So I'm going to be on y bar and change it in the x direction. Okay? Look what happened. What changed? Right? The slope flattened, which by nature, if the slope flattens, the y-intercept's got to change. So it changes both. What does that mean? Well, it means that an outlier in the y direction only is just going to pull the line up. So it's not going to change the calculations a lot. It's going to change the y-intercept, but that's not going to change slope very much, or at all. An outlier in the y direction only is going to change both, and so therefore really change your calculations as far as your regression equation goes. So an outlier in the y direction only is not influential, but an outlier in the x direction only is. Okay? Now, if you're asked to predict what's going to happen to the regression line, you can think about these points as having a string tied to them, and they're all pulling on the line, and the strength of their pull depends on how far away they are. The farther away from the line, they're going to pull harder. And then you can also consider this line like a teeter-totter, right? And the hinge for that teeter-totter is right there at x bar, y bar. Well, if I put a dot right above that hinge, then the teeter-totter is not going to move up and down. Right? It's not going to move. It's not going to teeter or totter, right? It's just going to be pulled up. So therefore, again, another reason, so what's going to happen? Our slope's not going to change, but our y-intercept will, right? If I put it up here, y-intercept will increase. Slope will stay the same. If I put it down here, y-intercept will decrease. Slope will be the same. But if I stick a point here, then this point is going to pull on this line on the very end. And when it does that, it pulls the line down, therefore it's affecting slope and y-intercept. Okay? And the same thing over here. It's going to pull it up, increase y-intercept and decrease slope. So you can always consider that when trying to guess as to what the point's going to do in order to change things. Okay? So back to our question about what is an outlier, what is an influential point, and what's the difference between these two, right? So an outlier deviates from the overall pattern. It affects R, we just saw that. An influential point is an outlier. And it's going to, in order for an outlier to be an influential point, it would have to adjust or affect both the slope and the y-intercept of the regression equation. Because as an outlier already, it's going to affect R. Okay? So to wrap this up, the difference, an influential point is an outlier that not only affects R, but also changes the slope and y-intercept of the regression equation. Okay? Now, as we just learned from the applet, as we just saw in the applet, an outlier in the x direction, in other words, an outlier that is away from the x bar line, will be more influential, or will be influential. I don't need that comma there. will be influential. More often than not, it all depends on how far away from the X bar line it is, and I can't write influential. An outlier in the Y direction, again away from the Y bar, so up and down, will not be as influential. Okay, so just some things to think about. And again, the difference is when you're considering an outlier is obviously it's going to affect R no matter where it is, although we could always investigate the fact that an outlier in the X direction will not affect R as much as an outlier in the Y direction, but at any rate it will affect R. And then depending on where the outlier is, it could be an influential point. An outlier in the X direction will be more influential than an outlier in the Y direction. And it has to do with that sort of pulling on the line hinge kind of thing that we just talked about. Okay? All right. So the last question that we haven't talked about, again, what should you always do before calculating the correlation of least squares regression line? We're going to investigate that in class tomorrow very quickly, and we'll answer that question together. You can work on the homework that I'll send out with the text, letting you know that the notes are posted, and then we'll start working towards getting ready for the test. Okay? Enjoy your night, and we'll see you guys tomorrow.